Hello everyone, today we will simulate a free-fall auto droplet problem in Ansys Fluent using VOF method. So let's get started. We are launching our workbench. So it will take some time. It's now 5:23 a.m. in BD, 25 September 2025, and we are enjoying our 14th week of third year second semester at Asanullah University of Science and Technology mechanical engineering program. So let's get started. So from here we will select fluid flow fluent, and we will actually fall a 15 millimeter diameter free fall droplet. So for this we will create a fluid domain. So let's start with new design modular geometry. So it will take some time, obviously, as my configuration is very moderate. So it has open, so we'll press, and for creating a domain we'll select rectangle. First of all we'll choose unit to millimeter, then rectangle, zoom in, then we will select center position, then draw a rectangle. Now we will put the dimension. So for our case, the dimension, actually the height is 5000 millimeter or 5 meter, and the width is around 150 millimeter. Okay, so this is the domain. So what we'll do now is click on generate, then we'll select concept, surface from sketches, then we'll select this axis line and apply, and then generate. So our domain has been created, and we will select it as fluid domain. As droplet is falling, there will be air in the domain, so so we'll simply cross or cut the portion, then we'll generate mesh on this. So let's get started with meshing. It will also take time. So our window has been opened, so it is loading actually. So this is yes. So for now, for meshing, we'll select on mesh, and for our case we will select the element size 1.25 millimeter, and we'll do nothing. We don't need to do nothing but element size, and we'll insert just a method. We'll select the entire region, apply, and this will be quadrilateral dominant. So for now we will generate mesh. So it will take time, actually it will take time. So I am cancelling it. I have a loaded file. Okay, so you can create domain, right? You can create domain, and you can generate mesh. So it will take time. This 5000 millimeter height and 150 millimeter width will take much time, around 3 to 4 hours. So for now I will open another file. So it is actually 8 millimeter droplet falling file. So the domain length here actually 2800, domain height 2800 millimeter, and width is around 75 millimeter. So you just need to create the domain for your case actually. So our domain has been created. If you follow the previous task what I have did before opening this, and from here we will go to simply setup. Okay, so if you are using very good CPU, so you can use solver process tree. For now I am choosing to start. So it will take some time. We actually I will cut this. I will firstly show the mesh for name selection purpose. So I am opening mesh. So I am cutting this one. So this is our domain actually. For your case you can choose different height width domain. So assume this as 5000 millimeter height and 150 millimeter width. So I have generated the mesh. It has taken enough time. So this is our pressure inlet for, we are actually there was a file we got here, the pressure inlet was this. So I have chosen the pressure inlet as this. So in my thinking it actually works like this, that horizontally pressure doesn't change, this is actually 101325 Pascal. So this pressure is not changing, but pressure changes in vertical direction in z axis. So there we are assuming that we have gauge pressure and our droplet will fall in this wall actually. So this is our fluid domain, entire domain is there. So this is actually the name selection process. Okay, I am cutting this. For showing you the setup, I am actually resetting the setup for again doing this, and okay. So our server process, for my case Core i5 11 Gen, I am putting 2, then start. I am okay. So this line indicates the pressure angle actually. So for our case we will do this in transient simulation process. This means things are actually changing with respect to time actually, and this will be same. 2D space is planar, our case. In axisymmetric, this means we have symmetric walls. So we will just put the gravity here, which is negative 9.81 downwards y-axis. Okay, and for model we are using VF model. We will select VF, then we will choose the implicit. So there are two options in formulation, explicit and implicit. So explicit actually means uncoupled with momentum and pressure equation, which means unsteady simulation. Okay, and implicit actually solves, explicit actually solves the momentum and pressure equation individually, and in implicit formulation pressure and momentum equation solves together. So implicit scheme is coupled with momentum and pressure equation, and this pressure applied to a cell volume actually. So we'll choose implicit method here and we'll select implicit body force. Okay, then apply. Then our face portion will be open, and for selecting the phases we'll select the materials first. For material we will go to fluid, new, and we will select water from here, water liquid, then copy, close, save and change and create, close. So now for going to VOF method, we will first select our viscous model, which is laminar for our case. Okay, then we will name the phase. The first phase is air and the secondary phase is water liquid, so we will select water and we'll simply click to apply. Then in phase interaction, we will on the surface tension modeling, continuum surface force and all addition, and we will put our surface tension coefficient for air and water. It is 0.073 Newton per meter. Then apply, then close. So now we'll move on to boundary condition actually. Okay, so for boundary condition, interior fluid, there is nothing have to put, and for pressure inlet, we'll simply select the gauge pressure to 0. Okay, this is our physics here. So for surface body, there everything must be same, no slip condition, stationary wall, and air water contact angle we know is 90. And for aluminium, for droplet falling in aluminium surface, the contact angle will be changed. For actually for different surfaces, the contact angle will change for different liquid and different surface. So for our case, we'll choose OK, then wall. So this on same as surface body, apply. So there is nothing to change in boundary condition. So we'll go to method. So for method, we will use simple. You can do trial and error for choosing methods, solvers for your case. Just you need to do some study before starting your case. So for here we are using volume fraction compressive, and now we'll move on to cell register, new region. From cell register portion, we will actually create the droplet. Okay, so we'll select circle, and x center means this is our x. Okay, so this length width was 75, so x center means center of x, so 75 divided by 2, we got 37.5. 37.5 millimeter means 0.0375 meter. Okay, for y we have this height is actually 2880 millimeter, means 2.88 meter. So for our case, we will y center means from where the droplet falling will be start. Okay, so we will simply choose 2.880, so 2.795. okay, sorry, it is 2.88, not 2.880, 2800. Okay, 2800 millimeter, so it means 2.8 meter. So for falling for the fall of this droplet, we will just we'll start from here actually. So this works actually like this. In the bottom portion we have 0, and in there we have 2.8 meter actually. So we are choosing droplet from some below portion of the top face actually. So our droplet radius is 0.004 for our case. Okay, you can select different types of droplet by for your case actually. So we'll simply click on save display. So save. uh, See, we have created a cute droplet. That's great. And we will now go into initialization. Go to initialization, then hybrid initialization, then we will select initialize. Then we'll patch the droplet because we need to see its behavior. So this phase is actually water, and we are using volume fraction method, and the volume fraction of water, here there is actually full water. So from so for full portion of water, the value of volume fraction is 1, and we are selecting the region. We have created region 0 as our droplet. So we'll patch the water to this region. Okay, we'll simply select patch. So we have patched, and for viewing this, we'll simply select contour, then phases, we'll select water, and we'll select the surfaces, all surfaces from here, and we'll select save and display, compute, save and display. So we have created our domain, and there is a droplet in the center of our domain, which will fall actually. So we will close this. So for run calculation, so before going to run calculation, we will go to report definitions. Okay, there is control, you can control things here. So methods, this is okay. And report definitions means here we can create graphs when we are running our simulation. So if we want to plot velocity graph, then we will go to report definition, new surface report, area weighted average. Then from here we will simply select velocity, and if we want to see the velocity of y velocity, actually the velocity of falling droplet, we will select y velocity, then interior fluid. Print to console means when you are running the simulation, it will show up here. Okay, so we are selecting this. Okay, so you can select different report definition for your cases. So for now I am selecting this one actually. And for calculation activities, if we I want to save the animation, I will go I am going calculation activities, solution animation, and then I am selecting my contour, okay, which I have created here. I have shown it. I have created contour here. You have already seen this contour. So I am clicking solution animation, then contour 1. Use active means when the entire simulation is running, it will show this face, only this face, if we this contour actually when we use active. This is actually fixed. So contour 1 is our view 0, which is fixed. This will show when simulation is running. We'll select OK from here again. So we are using use active. Okay, so contour, front view, use active. So rename the sequence file. Okay, they are telling us to rename this. So animation, what can I say, 8mm droplet. So contour 1, use active. Okay, right. So simply we will now run the calculation. So here interesting things will happen. For our case, we are, for this case actually 2800 2800 millimeter height, uh, domain and 75 millimeter width domain. I am choosing time step is 2250 2225 actually, sorry, 200 to 2250 actually, and time step size I am choosing 0.000016, and maximum iteration per time step means the calculation will update after 20, actually 20, after 20 time step. So from I am now opening calculator for showing you some things. For from here, if I elaborate maximum iteration per time step, this is actually means in one time step there will be 20 iterations, there will be 20 calculations, okay. And for number of time step and time step size, we can calculate our simulation total simulation time, means what we are actually seeing, okay, for what we want to see actually. For our case, if we multiply these two, number of time steps 2250 into number of time step size 0.00016, we'll simply get a number which is actually our desired time. This is actually the time the simulation we are seeing. The simulation actually we are seeing the simulation for 0.36 seconds. So this is the actual effect of simulation, actual time. But our when we will create animation, this animation size can be higher than this, because this is actually effect. We are seeing the effect. We actually want to see the effect of 0.36 seconds, so you can understand this. So now we'll move on to slide for some understanding. So understanding of courant number. So courant number simply means velocity u into grid size x into divided by del t. This means this delta t means time step, this delta t means this time step size, okay. For our case it is 0.00016. so this delta t we can select or vary this delta t. And from mesh, for structured mesh, we actually the mesh is actually the broad term, okay. Mesh can be anything like this, triangle, rectangular, anything. For a structured mesh, we actually call it's a grid, okay. These things actually grid. So in our case, the mesh is actually like this, the structured one, and here we have selected the mesh size 1.25 millimeter. So this actually means the grid size equals to delta x, okay. This actually means the grid size. For unstructured mesh like triangle and rectangular, hexagonal, it can vary actually. So for our case, our mesh size is equal to del x, equals to grid size. For our case of velocity, we can say time is equals to root over 2h divided by g. this we have got from high school physics, uh, the following formulas of Galileo's. Okay, free fall formulas of Galileo's, or laws of Galileo's, free fall laws. So T is actually this, and from we got another equation, V equals to U plus GT. From this U, actually the initial was initial velocity, which was 0, and V equals to actually GT. So from our case, we got the time, and the time, if we calculate like root over, so let me calculate. Oh yeah, we can calculate it on our calculator. So root over bracket, so I am calculating this on our my manual calculator. You can calculate this on your calculator also. So basically, if I put the values for our case, the H was 2.8 millimeter, but we are started the falling of droplet. We have started the falling from 2.975 millimeter. So we will actually put H as 2.975, sorry, meter. So this should the units should be same. Actually, for now we are on SI unit. So G equals to 9.81. So T here is 0.778, and V equals to GT from here 9.81 into 0.778. we will get the velocity. 0.778 into 9.81, this is 7.63 actually, 7.6 actually meter per second. So for now we are choosing U as this 7.6. so I am removing everything from here to calculate the current number. So for our case, the velocity is actually, for free fall droplet problem, 7.6 meter per second. The velocity, the end velocity actually. So I am removing this, and we will simply calculate the current number. So after that we will make some decisions. So this is 7.6, this is 1.25 millimeter in meter, which is 0.0125. okay, sorry, 0.00125, it will 0.00125, and delta T is this 0.000016 or times 0016. So from here, if we calculate 7.6 into 0.00125, 0.00016. So actually we have done some error here. Basically the current number formula, there is an error. The T, time step, will be here. Okay, the delta X will be here. So this will move to down. Actually this will move to down. So here we will get 0.00125, and here we will get the time step size 0.00016. So after calculation, so let's calculate first. 7.6 into 0.00016, 0.00125. So our current number is 0.97 actually. So if you are using implicit method or implicit formulation, implicit, so this current number doesn't matter sometimes. Actually this is flexible for implicit formulation. If you are using explicit, which means what? Unsteady. Actually unsteady simulation cases, the current number should actually less than 1. The current number should must be less than 1 for getting the current number must be less than 1 for getting a stable simulation. So this is the significance of actually current number. You can study it further in online, and you can read some papers on it or from different sources. So for now we will move on to here, and from these things, after putting these things, simply we can uh, click on calculate. So the simulation process will start. So I am clicking on calculate for showing you the demo, but I will not run it entire time. And for getting more infos, we are actually selecting data file quantities, and we are selecting all quantities from here because it's important. We if we do not know what quantities we actually want, so selecting this all is a good option. Okay, so if we click on calculate, the simulation will start. So we'll select a velocity graph. So this is our actually velocity graph. In y-axis we are getting y velocity. This is actually y velocity versus flow time graph. This is our contour, this is our residual or error graph. And here we will actually see the simulation, full simulation. The droplet will fall when this progress this is the simulation progresses. When the simulation progresses, the droplet will actually fall. So for 100% it will not complete the whole domain, but it will, as the number of time step is we have taken it low, so this will go actually 1/4 portion approximately. Okay, so if you have a very good computational setup, you can put the time steps in higher numbers, and you can show you can get the entire simulation for that. So for now I am stopping it. You can, if you want to continue it further, you can stop at the end of time step, or simply if you want to do not if you do not want to edit these files or do not want to change things, so you can simply click stop iteration, otherwise stop on time step. Okay, so after getting after solving this, we'll get like this one animation, like this animation. So this animation is actually for a 30 millimeter water droplet with a channel height of, or domain height of 5000 millimeter and width of 150 millimeter. For your case, the animation will come actually. So you can save this animation from by when your calculation has been completed, you can go to animation, playback, then you can simply run it choosing the frame rate, and you can write the video. For before that, you have to select video file, then write, then it will save in your workbench default folder, or Ansys default folder actually. So this droplet will fall when you see the animation like this. So this is actually very soothing scenario. Okay, soothing scenario. So that's all for today, everyone. These things actually, we are not actually doing things here, we are actually solving physics, we are working with physics. So this thing is actually a type of feeling of interfacial science, where the interfacial science start the interaction of fluids or multiface problems via methods. So that's all for today. Thank you everyone. Pray for me. My name is Tanvir Hassan. Pray for me, so I'll upload it to my YouTube channel.